Okay, Dhruv, we will start with that question then. Question number 12 from HC Verma. Let's begin with this. So all of you go through the question, please. I'll explain it in a moment. Okay, let me explain the question. So it says that a boat has an internal volume of 1 meter cube and a weight of 50 kg. Neglecting the thickness of the wood, find the fraction of volume of the boat immersed in water. If a leak develops in the water, so this thing that they've said, neglecting the thickness of the wood, that is more applicable for the second part actually, not so much for the first part. Question number 9 also, okay, we'll discuss. Okay, so yes, we'll discuss doubts from the major test too, but let me finish the HC Verma doubts first. Okay, so let me start with question number 12. I'll go back to the earlier questions. So it says that the boat has an internal volume. So internal volume se kya matlab hai? Of 1 meter cube. It means that, you know, if you look at the cross section of the boat, it's like a traditional style boat if it is like this, and is floating like this with a certain part underwater. Then the internal volume is like the capacity of the boat. But at the same time, they are asking to neglect the thickness of the wood with which the boat is made. So the internal volume is more or less equal to the external volume. So So basically, the internal volume would be this shaded portion which I'm showing. This shaded portion's volume is the internal volume, but it's saying to neglect the thickness of the wood it's made with. So neglect this part. So the total volume only we can take as, whether we take it as the internal volume or that is more or less equal to the total volume of the board. Board is like a shell, an open shell kind of thing, and that is 1 meter cube. And its mass is equal to 50 kg. So hope the meaning of the question is clear, Dhruv, now. So this is buoyant force and the downward one is the weight. Okay, so that's what he meant by saying that neglect the thickness of the wood. So we have to take this outer volume only as 1 meter cube. Now what is happening? The submerged volume that is given to us as oh, that we have to find out. Okay. And we have to use the density of water as the standard thing, 1 gram per cc. So it's not given in the question, but we just use the standard value. Okay. So this is not going to be of importance in the first equation. In the A part, we have to just find buoyant force equal to mg. So density of water into submerged parts volume into g should be equal to mg. So 1000 into whatever the submerged volume in meter cube, g we can cancel on both sides. This should be equal to 50 kg. Okay. So as you can see, this is in kg per meter cube. So you'll get the submerged volume in meter cube. Okay. So you get the submerged volume as 50 divided by this much. So 1/20th of a meter cube. Okay, so quite extraordinary. So I mean, this is kind of going to be a very stable kind of boat. Now only 1/20th is going to be submerged, or maybe is assume the shape is extremely conical like this. So even if some part like this is submerged, in terms of ratio of volume, it's quite a bit less because the shape of the boat is tapering. So maybe it's assume something like this, but typically it will not be like this. A much larger fraction of the boat's volume is submerged. Anyway, so the first part, the fraction of volume submerged, there will be 1/20th of a meter cube divided by 1. So that's why I said it's rather extraordinary answer. So 1/20th part of this is submerged. Okay. So now you must have understood what's happening in the B part. Now in the B part, if water leaks in and it's about to just submerge. So let's say this much part is filled with water and it's about to now submerge. So on the outside, the water level has reached more or less the top. Okay. So what has happened is that the weight of the boat has become some m prime, which is mass plus the delta m, which is the mass of water which has leaked in. Leaked into the boat. Okay. And this is some new value of buoyant force. Now, new value of buoyant force is the maximum possible buoyant force before it sinks. Maximum possible upthrust. So it is just about less than equal to the density of water into the full volume into G. So this maximum buoyant force should be equal to the new value of weight. Okay. So this thing will become 1000 kg per meter cube into 1 meter cube should just about have become equal to m plus delta m into G, where you put m as 50 kg. So you can find out how much delta m is. So the question is clear, and what method you have to use, that's also clear. So once you find this delta m, now you can find the volume of water which has leaked in. Okay, this is the mass of water which has leaked in. So if this mass is delta m, then the volume of water which is leaked in is this mass divided by density of water. So this will be the one. Okay. So Dhruv, I think you can manage the question from here, right? Okay. Now Samarth has asked question number 1 and Shikhar has asked question number 4. So let's discuss these two also. Jagannath, you can just note down the method I give you and try out the full numerical problem later, because we have to cover a lot of things today. So go through question 1. So question 1 is basically like this. You have to find the hydrostatic pressure. So let's say you have water at the top of a building in a tank. So this is what the situation is. So let's say the tank is attached somewhere by the ceiling over here in a building. And this is the ground level where the tap is present. So some kind of a pipe is bringing in the water. Has given to us that the level of water in the tank is such that it is at a height of 4 meters with respect to the ground level. So when I open this tank, water will gush out because of this pressure difference. In fact, very soon in hydrodynamics, we'll be studying the speed with which water comes out as a function of the pressure difference. Okay. So if the point just inside the tap is the point A, we'll see that the pressure at the point A will be atmospheric pressure plus rho GH. So the hydrostatic pressure or the water pressure, so called hydrostatic pressure at A, which we generally write as delta PA, that is just rho GH. So that is density of water multiplied by 10 multiplied by 4. So you can see it's so many pascals or approximately 0.4 atmospheres. So this is the amount by which the pressure of water inside the tap exceeds that normal atmospheric pressure. This pressure difference we will study later is what is responsible for water to come out when we open the tank, because there's larger pressure inside and lesser pressure. Now the second part of it, is it necessary to specify that the tap is closed? The proper answer to this we will understand only after going through hydrodynamics, the second part. But as of now, I can tell you this, that if it is like a, the area of cross section of the tap is very negligible compared to the area of the tank. That means when we open the tank, the rate at which level of water is coming down is very, very small, because very less amount of water is coming out from here. Then it doesn't matter whether the tap is open or closed. Whereas if it's a very wide opening, so the moment we open the tap, water starts coming down rather rapidly in the tank, then it will affect the pressure difference. Okay. Now, why exactly will affect, we'll understand after studying something called Bernoulli's equation. So that part becomes like a hydrodynamics question. Anyhow, so hope the question is clear. Okay, we'll discuss question 8, 9, all these two. Okay, Samad, good. Let's come to question 4. Now, question 4 is an interesting question. It is based on, the solution of question 4 is completely based on the hydrostatic paradox problem. Remember, we had discussed about it, I think in the second lecture or maybe last lecture. But the 3 types of vessels, the conical vessel, the cylindrical vessel, in that, how it works. A similar concept over here. Then we also did a question where we had that conical vessel and we wanted to find the weight of liquid inside it, using the, so there we use the formula for volume of a cone and all that. From that, we found out the net force due to the side walls. So this question is a much easier version of that question, because here directly the volume of the container is given to us. Okay. So if you look in the question, what is happening? You have this, typical type of shape of a container, like a fish bowl kind of shape. So it's got like an open cylindrical top like this, and then a closed cylindrical bottom like this. So it's like the volume is more than just the volume of the cylinder, because there is some bulge on the side like this. The glass container, some bulge like this. Okay. Now the data which is given to us is that this height is something 20 centimeters, and this area of the bottom disc is 20 centimeters square. But at the same time, it is also given to us that the volume of the container is half a liter. Okay. So that is the same thing as 500 milliliters, or that's the same thing as 500 centimeter cube. Because as I told you before, you should always remember the relation that 1 cubic centimeter is equal to 1 milliliter. And that's why 1 liter is equivalent to 10 raised power 3 cubic centimeter, which is the same thing as 10 raised power minus 6 into 10 raised power 3 meter cube. So the standard unit is like this, that 1 liter is 10 raised power minus 3, or 1,000th of a meter. So 1 meter cube is the SI unit, as you know. So anyway, it's 500 cubic centimeters, or half of liter. So you can see that the volume is considerably more than the volume of this cylinder, because this cylinder is 20 into 20. It's 400 cc. So the remaining volume is over here. Okay. So if you fill this with liquid now, the volume of fluid. So I think that's water only. So the volume of water is 500 cubic centimeters. So accordingly, the mass of water, that is 500 cubic centimeters multiplied by gram per cc1. So it's 500 grams, or 0.5 kg. Okay. So that is the mass of the water. Now it is given to us that the first thing is we want to find the force by the water on the bottom surface of the tank. So this force, so on the bottom surface, the force will become pressure due to water, that is the hydrostatic pressure, not the net pressure, into the area. So that is rho gh into this area. So again, in SI units, 1000 into 10 into h is 0.2 into the area, which is 20 centimeters square. So 20 into 10 raised power minus 4. So this will be the force in newtons. You can see that is, I think there's 4 newtons if I'm not mistaken. Yes. Okay. Whereas if you look at the weight of the liquid, that's very interesting. That's actually, if I take GS10, it's 5 newtons. So the explanation to the difference in the weight and this is that only, that if you think of the free body diagram of the water, you have this kind of volume of water which is inside this. Now this is experiencing a normal reaction from the bottom, which is equal to this force F, which is equal to 4 newtons. Okay. But you can see that is falling well short of its weight, because just now we've seen its weight is equal to 5 newtons. So the mass of liquid we saw is. So that's why I said this is an easier question, that to calculate the net force due to the side walls, luckily we don't have to do any integration type of calculation. Understand logically that this force due to pressure on the liquid because of the side walls, there will be vectors like this. So you can see that the upward components of the vectors will dominate and the horizontal components will cancel. So if this F prime is the net force due to side walls, then we can calculate this F prime quite easily by using the relation that F prime plus this normal reaction together is balancing the weight of liquid. So F prime becomes approximately 1 Newton. I said approximately because I'm taking G as 10. HC Verma might have taken G as 9.8, in which case the answer would be 0.98. Oh, he's asked to take G as 10. Okay. Okay. So very good. So hope this question is clear. Just check the answer once. Yes, 1 Newton upward is the net force. So Shikhar, hope you understood the vector diagram. Okay. Achha, okay. Wait. So the first part, let me read the question again carefully. First part may not be talking about force due to hydrostatic pressure. It might be talking about net force. Let me just check. In which case we have to include the atmospheric pressure also. It says find the force exerted by the water on the bottom of the tank. It's not due to hydrostatic pressure. It's the net force that the water is applying. So this is the force due to hydrostatic pressure. Okay. This is force due to hydrostatic pressure. But if you consider the force due to the net pressure, on the bottom surface, it will be the absolute pressure, that is P naught plus rho GH into area. So you'll get your answer. Sorry, this is 10 raised power 3, 10 raised power 4. This rho GH factor, you can see, this is this is 2 into 10 raised power 3, like this. Okay, so this is 102 into 10 raised power 3 into 2 into 10 raised power minus 3. So that's why it is 204 newtons. Okay. Now, if you want to go with this explanation of understanding what's happening over here, when you make the FPD, so it is like a more complete description of it. For the free body diagram of the liquid, it's like this is equal to F net, but then there's also pressure force due to atmospheric pressure, which is this. Okay, and this is equal to this. Okay, and then there are the other forces, the weight and the force due to the side walls. So this you'll see becomes equivalent to this diagram only. So because of the weight of the liquid, how much normal reaction the bottom surface is applying on it, that is equal to the difference of these two forces. Because even if I remove the liquid, there is that much force P naught into area acting downwards on this. Okay, so basically this normal reaction is equal to this F net minus F naught. Yeah, so in the second part, Jagannath and Shikhar, what is happening is, see, you make the free body diagram of the liquid. No? The liquid in the container, if you think about it, that is a certain amount of material, certain mass of material, which is at equilibrium. So the net force on this should be 0. So this is the FPD of the fluid volume actually, which is the amount of water which is present. So that volume is of mass we had seen earlier, 0.5 kg. Okay. So what all forces it is experiencing? It's an open surface. So from the top, it is experiencing a force equal to atmospheric pressure into area. From below, it is experiencing a force which is equal and opposite to the force F net that we had calculated, which is absolute pressure into this area. Okay. And then from the side walls, because the pressure of the liquid is pushing the side walls like this into them normally. So these are applying equal and opposite force like this. But as you can see that with depth, what happens? The pressure increases. So the further down you are, the larger the value of the force, because the pressure is more. So the force vectors look like this. They are normally into the surface, but with magnitude decreasing as you go up, because pressure increases with depth, decreases as you go up with height. Okay, so these are the force vectors that are acting on the side walls. Is this clear now, Shikhar
Yes, sir.
and Jagannath both? No? Okay. No, buoyant force क्यों होगा बेटा यहाँ पे? Buoyant force तो when an object is submerged inside the water, ना? So this is like the net force that the side walls are applying. These vectors combined, okay, a vector like this and a vector like this, their x components will cancel and their y components will add. So like that, all these vectors together are applying a net force upwards. There's no question of buoyant force here because there's no other body which is submerged in the liquid. This is the liquid body itself, so it does not apply buoyancy on itself. But this F prime over here is the net contact force applied by the side walls. Okay, so this is clear. The direction of it, why it is vertically upwards. Achha, good, you understood now, no? Okay, so now the equilibrium condition is that F prime plus this F net should balance the other two vertically downward forces, which is F naught plus mg. So F prime should become mg minus of F net plus F net, which we can write as mg minus of F net minus F naught. Now this only is equal to that normal reaction thing that we calculated, which was rho gh into area, which was equal to 4 newtons, whereas the weight was equal to 5 newtons, taking g as 10. So that's why the net force due to the side walls is becoming the difference of the two. So that's 1 newtons upwards. Okay, so hope this is fully clear.
Yes, sir.
Okay, very good. So this is that interaction force with the side walls. All right, now let's move on. So that was question 4. This is one of the important questions. Okay, the slightly tricky type of questions. Okay, question 9. I think somebody else has asked for question 8 also. Yes, Shikhar. And Jagannath, question number 6 also. Okay. So let's look at these questions next. 6, 8, and 9. Six is which one that? If water is to be used to construct a barometer, what would be the height of the water column at standard atmospheric pressure? For mercury, it is 76 centimeters of mercury. So the working principle of barometer, which you can see is also given in HCV plus. I think we discussed once during fluid mechanics, during heat and thermodynamics. So what we have in a standard barometer, which is a mercury barometer, is that you have a vessel like a large beaker kind of thing filled with mercury first. And mercury has a standard value density of 13.6 gram per cc. Now, next what we do is we take an we take an glass tube like this, which is open, whose length is slightly more than 1 meter. So that when we keep part of it dipped inside the mercury beaker, we can keep the column outside equal to 1 meter in length. Okay. So we fill this up with mercury right up to the top. So this length is slightly greater than 1 meter, just a little bit more than 1 meter. So then what we do is we seal this open end, okay, invert it. So first we seal this open end, invert it, and then place it into the container like this, okay, such that the closed end is above. This is the closed. So this is the closed end now. The open end is inside, but remember initially we had sealed it. Now, after putting it like this with the closed end completely submerged in mercury and making sure that the section outside is exactly equal to 1 meter, okay, then we open this seal. So as we open the seal, what happens? The mercury that was filled right up to the top initially, its level drops because of the pressure difference. But as its level drops, here there's a vacuum column formed. Especially because usually we keep this part of mercury covered with some foil and all that. So air bubbles cannot escape here and come here. So this is vacuum. So if the mercury level comes to equilibrium for some x, then we can see that this point's pressure should be equal to this point's pressure. So pressure at the point E should be equal to pressure at the point B for the equilibrium. Now pressure at the point A is the pressure in the vacuum column, which is 0, plus the pressure difference because of the mercury. So that is rho gx. And the pressure at the point B is, it's an open surface, so it's atmospheric pressure. So this is how we measure the atmospheric pressure. It is density of mercury into G into the value of x in that column at an instant when it's in equilibrium. Okay. So at standard sea level, x comes out to be 76 centimeters. So atmospheric pressure comes out to be 13.6 into 10 raised power 3 multiplied by 9.8 multiplied by 0.76 when we convert to SI units. Okay, so this is the standard functioning of a mercury barometer. So this comes out to be approximately 1.1 into 10 raised power 5 pascals.
1.01.
Yes, 1.01. Yes, which is 1 atmosphere, or we also call it 1 bar sometimes. Okay. Now what they are saying is replace the liquid in this with water. So we replace the liquid with water. What is the height of the column we'll require? Then this formula will remain that rho gx is equal to atmospheric pressure, but this rho will be density of water, which is 1000 kg per meter. So we'll have x's value as atmospheric pressure divided by g into 1000. Okay, and we already know that the pressure value is 13,600, okay, into G into 76 into 10 raised power minus 2 in SI units. So that should now become that divided by 1000 into G. So obviously the value of X, the density I've used is of water, which is 1 upon 13.6 times the density of mercury. So obviously the height will become 76 centimeters divided by, into 13.6. Okay. So this is the height of the water column if we use a water barometer.
So can you explain how did you get the value of x at 76 centimeters?
That is the standard value, beta. I mean, if we do the experiment at sea level, then the standard atmospheric pressure's value is such that the mercury level drops up to 76 centimeters. Okay,
Okay,
so
sir.
that's an experimentally observed value. Is it clear, beta?
Yes, sir.
Okay. Okay, now let's move on. Yeah, next we are doing which question now? We are doing 9th, 8th. Okay. I missed question 5. Okay, fine. Let's go through question 5 also. Okay, so it says in core only, if the glass of the previous problem is covered by a jar and the air inside the jar is completely pumped out, what will be the answers to the problem? So in question 4, okay, where I had the open jar of glass with a closed bottom and I filled it with water. Okay. So I saw that this force, this net force that the water is applying, it became the net pressure, which is the atmospheric pressure plus rho gh into area. But the force that the side walls were applying, that force when we calculated formula wise, that had come out to be rho gh into area, because that was basically equal to F net into area minus F naught into area. So this F prime had come in terms of this. So it's mg minus of this thing. Okay, now instead of this, in the 5th question, which Samarth has asked, if what we do is, we got this open vessel, we fill this with water up to here, but now we've also closed this with an airtight lid and we vacuumized this part. So we closed the top with a airtight lid kind of thing and we pumped out the air which is remaining over here. So then what happens? This part's pressure becomes 0. Okay. So what is happening? The net force now exerted by the water is actually the force due to hydrostatic pressure. It is pressure at that point into area. So that is rho gh into area. So in this case, that would have become that 1000 into 10 into 0.2 into the area of 20 into 10 raised to minus 4. So that thing that we are getting 4 newtons. In this case, this would be the net force that this is applying. But when I consider the net force applied by the side walls, that would not change now. Because when I consider this time, the free body diagram of the liquid, there is no force on the top because the pressure is 0. So even though this now changes from a value of 204 to only 4, but there's no 200 Newton force from above because there's no atmospheric pressure. So the answer to the force due to the side walls, that doesn't change, that remains the same. So the net force due to the side walls, this still remains 1 mu. So hope this is clear, Samarth. Okay, very good. Let's move on to question 8. Question 8 is, I think, based on one question we've done in class. Okay. So I'm just going to discuss the part which I've not done in class, which is the torque part. I'm sure you found the net force on the side walls by that method of integration. Anyhow, let's check it out. So rectangular tank size is 3 into 2 into 1. Okay. Side wall is of dimension 2 into 1. Okay. That means the bottom surface is of dimension 3 into 2. Okay, so the interesting thing now is that we don't know which one is the vertical height and which one is the side length. No? It could be the bottom surface is 3 into 1. Anyhow, let's make an assumption that is 3 into 2. So in question number 8, we have that typical kind of situation. We have a rectangular tank. Which is filled with water to the top. Now it's not exactly given which of the dimensions are horizontal and which one is vertical. So we'll just make an assumption here that the dimensions given as 3 into 2 into 1 meter. So this is 3 meters, this is 2 meters, and this 1 meter. We'll just make that assumption here. Now water is filled to the top. Okay. And we want to find the net torque on this side wall. So let's say on this side wall, we want to find the net torque due to hydrostatic force about the bottom edge find the total torque by the water on the side about the bottom edge. So if we consider this as our axis about which we are calculating the torque, about this axis you will see that the force due to the water pressure which acts like this on this side wall, this creates a torque like this. So we want to calculate this torque. Okay. So again what we have to do is we have to use integration. So we'll take a strip, thin strip at a depth of y from here and of thickness dy. So because of the hydrostatic pressure, how much force is acting on this strip? The force acting is hydrostatic pressure into area, which is rho gy into the area, which is L into dy, where L is equal to 2 meters. This one, this L. Now you can see that this force, when we look at it from the side view, this force is acting on the strip like this, where the strip is at a distance y from the top. But we are considering this as the axis of rotation. So with respect to this axis, what is the moment arm of the force? The moment arm of the force is h minus y, where h is the total height. This height is taken as h. So how much torque this force is producing about the bottom edge? This force into its moment arm, which is h minus y. So it is rho g y into L dy. That is the force multiplied with h minus y. That is the torque. Okay. Where h is this height, the vertical height, and L is the the side length of the wall, the horizontal side length of the wall, which is of 2 by 1 meter, like this. Okay. So the net torque that is acting about this axis is going to be integration of this. So we can take rho g common outside. In fact, rho g L can be taken common. We are left with y into h minus y dy, integrated from y equal to 0 to y equal to h. So this becomes rho g L. Now hy's integration is hy square by 2, and y square's integration is y cube by 3. And on this we have to put the limits y equal to 0 to y equal to h. So as you can see, becomes h cube by 2 minus h cube by 3 is the upper limit minus 0, which is the lower limit. So it becomes 1 by 6 of rho g L into h cube. So this is the torque on the sidewall, where we'll take the density of water as this much. We'll take G as this much. This length is the horizontal side length of the wall, which is 10 meters, and the height is the vertical height, which is 1 meter. So accordingly, we'll get the answer. Okay, so 2 or 3 of you have asked this question, so I hope this is clear. For the force, you just had to integrate the force alone. If I wanted to calculate the net force on the sidewall, I have to just integrate this. So that is integration of rho g L into y dy from y equal to 0 to y equal to h. So this derivation we had seen last time in class. But now from that we are calculating the torque. That is how. Okay. But this is not what is required in the C part. What is required in the C part is the torque. It's okay, it's a matter of nomenclature. So I've just taken that side to be L. Then your area will also change into B dy, instead of, if you take B as 2. The important thing is I've taken the length of the side of that vertical ball. That one I've taken to be 2 meters as given in the question. Okay. And yes, Durgesh, how we decided the base dimensions is because it's specifically given to us that the side wall is 2 into 1. So obviously the base is 3 into 2. No? So now that was question number 8. Just make a note of it if required. E part, okay. E part ही तो किया ना. Find the torque of the force calculated in part B. Okay. So actually C part is different. What I've done for you is the E part. C part is like, just a thing about that in C part, what, so this is actually part E, my mistake. In C part, what is they asking is that the force that just this one is applying, this dF, what is the torque because of that? So the answer to that is this one. Okay. It is dF into the moment arm, which is h minus y. And what is dF? It is In my diagram, it is rho gy into L dy. Okay. But if you have taken the dimensions like this, that you've taken this side as B, then just replace the L over here with B. But more importantly, its value is 2 meters. So this is the answer of the C part, that just that force acting on a horizontal strip like that, how much torque it's creating is this. So then from there, for the E part, we integrate the torque because of all these forces which are acting on all the strips. So understood the difference now between the C part and the E part, Jagannath? Okay, very good. Let's move on to the 9th question. Yeah, 9th question, I will just give you a hint. It's a pretty straightforward question once you understand it. Okay, very good. So those of you who have asked the 9th question, I will just give you an idea of how to solve it. So see, when the gold instrument is in air, whatever weight that you measure, okay, this is the measured weight in air, that is equal to the density of gold, okay, into the actual volume of gold which is present, okay, into G, plus there is an impurity of silver also. No? Is it silver or what does it? Yeah, gold and sorry, copper. So there is impurity of copper. So it is density of copper into whatever volume of copper is present into G. This is the true weight in air. And the volume of the ornament will actually become the volume of gold plus the volume of copper. Will be the, by volume, it is the amount of gold present plus the amount of copper present. Okay. Now, when you put this ornament completely under water, what happens? Its apparent weight, that becomes mg minus buoyant force. Okay. So this apparent weight is how much? It is 34 grams into acceleration due to gravity. It's actually mass given to you, not weight. Whereas the true weight, you can think of this term here as the true weight, because you're measuring it in air. So the true weight is actually, how much is it? 36 grams. So the mass is 36 grams. So this is this into G. Okay. Now in this, what is the buoyant force? Buoyant force is density of the fluid, which is water, into volume of the submerged part into G. Now in this case, volume of the submerged part is the total volume because you're completely submerging, which is coming from here. Okay, so two equations and two variables. The volume of gold is unknown, the volume of copper is unknown. Okay, so just substitute these two over here in this equation and you will get the answer quite easily. Just try this out. Okay, so here if you see the true weight, which is 36G, is equal to what are the densities given? 19.3 and 8.9. So that specific gravity, remember, is the same thing as relative density. So it is actually the density in gram per cc is equal to 19.3 into volume of gold plus 8.9 into volume of copper into acceleration due to gravity. So this is 36 grams. This is in gram per cc into this volume in cc. Same thing here. So we are being consistent as far as the units are concerned. So we have this relation that 19.3 into volume of gold plus 8.9 into volume of copper is equal to 36, where these volumes are in cc, cubic centimeters. Okay. Now secondly, we have mg is 36g, mg minus buoyant force, that is the apparent weight, that is 34g. So that means how much is the buoyant force? The buoyant force is 2g. Okay, so now let's bring this in. So the buoyant force is basically what? It is density of water into the full volume. That is the buoyant force, which is equal to 2g. Now the full volume is basically what? It is the volume of gold present plus the volume of copper present. So this is telling me that the density of water is 1 gram per cc into volume of gold plus volume of copper, or total volume, is equal to 2. Cancel of the g's. And now you have to just solve these two equations to find the two volumes. Okay. So this was the 9th question. Again, those who have asked this, I hope this is clear. After 9th, which was the doubt we had? We had discussed 12th. Anything else? There is one very interesting question which don't see anybody has asked over here. So maybe you have not reached that point, or better still, you have solved that question. But the solution is a little bit tricky, so I want to bring up that question. Actually, 10 and 11 also. Okay. Okay, we'll do 10 and 11. Actually, we'll do 11 then. Also, I want you to try question 25. It's very interesting. Just try out question 25. I'll discuss 25 and 11 together. In question 11, Jagannath, you have to just make a free body diagram. You have to understand that at the bottom of the container, where that metal piece is in contact with the floor of the container, it is not like a continuous contact. There are gaps. So there is gap for water to get in and apply buoyant force. So in an extreme situation, if I draw a very sort of this kind of shape, so you can see that the water that is present is not present only from the sides and from above. It is also in contact at the lower surface. And that is why it is able to apply an upward buoyant force. So the buoyant force that the water is applying, the weight that the object has, and the normal contact force that is acting through the points of contact, these three together should be in equilibrium. So this normal reaction force should be equal to mg minus buoyant force. So that should be equal to the density of the metal minus the density of water into the total volume of the material into G. Okay. So now see, in this it is given to us that the density of the metal is how much? It is 8,000 kg per meter cube. So that's 8 gram per cc. So given that the density of the metal is 8 gram per cc and the mass of the metal object is 160 grams. So from this you can see that the volume is 160 divided by 8 or 20 cubic centimeters. So the normal reaction will become this minus this into 20. This is per cc into cc. So this will be in grams. So convert it to kg like this into acceleration due to gravity. So this will become the normal reaction in newtons. Okay, Jagannath, is the question clear? Okay. Yeah. Okay. So this you'll get the answer from this. Now try question 25, all of you. We'll discuss in a moment. So you have that ice cube. Go through the question, I'll explain. Okay, so hope you try to figure out what makes the question very interesting is the geometry and how we do the calculation here in 25th. Okay, so you have this cylindrical glass vessel, okay, which is of where is the question?
So just one more minute.
This diameter of 6. Sorry, come again. You asking something, madam?
No, sir. Actually, I thought you were starting the question, so I just told you to wait one.
Okay. Okay, so initially we have this cube, which is of 4 centimeter by 4 centimeter by 4 centimeter. So initial volume of ice is this much, and volume of water is 0. Okay, and also this diameter is 6 centimeters. So now if you observe after some time, part of the ice is melted. The ice cube's own dimension has become smaller. Okay. And the ice which is melted, it has resulted in formation of a water layer. Let's say the water level has reached a level of height h. Okay. So at some instant, let us say this has become x. Now it's saying that assume that the ice melts uniformly on from all sides. So at some time, the volume of ice has become x cube in cc. Okay. So the volume of water formed is no longer 0. Okay. So that volume of water will be something into H. Okay. It will be some factor into H, where H is this height. Now on this, you want to find the condition for the normal contact force that the floor is applying, that to become zero. So that will only become zero when buoyant force equals to the weight. So the condition for the contact force to become zero is that the buoyant force becomes equal to the weight. So then you have to put this back over here and solve for H. And from that, you will be able to solve for X. That's what makes this question very interesting. So I'll just give you another minute or so to calculate this. So try to figure out how we can relate the volume of ice with the volume of water formed. Okay. What is this relation? Try to figure that out. Okay. And also try to figure out what we'll substitute here. That this volume of water formed is some factor into H. But what is that factor? So once you figure that out, you'll be able to substitute this in the buoyancy equation for the condition for the normal contact force to become zero. Basically for us to start floating. So remember that density of ice is 0.9 gram per cc, whereas density of water is 1 gram per cc. So when ice floats in water, 9/10 of the ice is submerged. Okay. Yeah, check. You can check your answer with the one given at the back. Okay. Okay. So by equating buoyant force with mg, so that normal reaction becomes 0, you'll realize that so this will tell us that the submerged volume, okay, so at least 9/10 must be submerged. So that means if you're looking at the ice cube, the height of water that is reached must at least reach 9/10 for it to lose contact with the ground or with the glass surface below. Got this point now? This height should become greater than equal to 0.9 times this side length, whatever the side length of the cube. Okay. So this is our first condition. Okay. Now the thing is, see the volume of water that is formed. When you see this from the top, you see the round cross section with the ice in between like this. So what is the area of cross section in which the water exists? This area, so volume of water, let's write that as VW, that is equal to this area into height. So this area will be what? It will be pi r square minus x square. This is the volume of water. So it is pi into 3 centimeter square minus whatever that x is, which we are going to calculate, into h. This is the second equation. Now also, we can say that mass of water is equal to mass of ice melted. Okay, so that means density of water into volume of water is equal to density of ice into original volume minus the volume of the ice now. So it is 1 gram per cc into this thing. This must be equal to density of ice, which is 0.9 gram per cc, into the original volume, which was 4 centimeter cube minus x cube. So this is like a third equation. So actually, we've already made use of the second equation. So this is the actual third equation. So we have substituted this over here into this. So that gives us this equation. So now we are very close to the solution. So we can see the relationship between these is this, that 9 pi minus x square into h should be equal to 0.9 into 4 cube minus x cube. Okay. Now the condition for normal reaction to become 0, we'll substitute that. Okay. Substitute from equation 1, the condition when n becomes 0 just about is when h becomes equal to 0.9x. Okay, so substitute that over here. So we have 9 pi minus x square into 0.9x is equal to 0.9 into 4 centimeter cube minus x cube. So luckily we don't have to solve the cubic equation because the cubic term will cancel on both sides. So many people make the mistake in this question of equating the volume of water with the volume of ice melted. But the volume is not conserved because the density is different. What is conserved is mass. Mass of water formed is equal to the mass of ice melted. So this is the volume of ice melted. And that is not equal to the volume of water formed. Okay. Because ice contracts as it forms water. So actually you can see from this equation that the volume of water formed is only 0.9 times the volume of ice melted. What is equal is the mass. So if you miss this 0.9 factor over here, you will end up trying to solve a cubic equation, which is going to be very difficult to solve also. Okay. So anyway, we get this 9 pi into 0.9x, okay, minus 0.9x cube. So on the other side, 0.9 into 64 cc minus 0.9 x cube. So the x cube term cancels out and we get the comfortable solution that x is equal to 0.9 into 64 divided by 9 pi into 0.9. So 64 by 9 pi. That's approximately 64 by 9 into 3.14 in centimeters. That is the side length of this. So anyway, this was the last of the questions of hydrostatics in HC1. There's also one question which is based on oscillation of a floating object. Since we will do simple harmonic motion later after doing fluid mechanics, so that oscillation question I'll be doing in that chapter. Okay, so this is nearly 2.264 centimeters. So the side length of the ice cube reduces from 4 to about 2.25 centimeters by the time it starts floating. Okay. So hope this question is clear. I'm just scrolling up and taking you to the beginning of the solution once. Oscillation one, I think it's the 23rd question, or I'll just check and tell you. It just directly asks you to find the time period only. So 23rd question, yeah, where you have the spring also attached. So you can do the first part, but the second part where you are asked to find the time period of oscillation, we have to use the simple harmonic motion concept, which we'll be learning in that chapter later. Anyhow, so this was the setup of this question. I'll take you through the solution once more. So this is the situation it's coming to. Initially, it was in a situation like this, where on the glass surface, you have the ice cube of dimension 4 by 4 by 4. But by the time it is reduced to x by x by x, you have a water layer around it. So the relationship between the volume of water and the volume of ice is this relationship. The volume of water formed is 9/10 of the volume of ice melted. You also hope you solved 14th and 15th question. Yeah, why we considered h to be greater than equal to 0.9x? Because for the ice to float, now 9/10 of it has to be submerged. So if the level of water is below 9/10 of x, how will 9/10 of the iceberg be submerged in the water? You understanding, Shikhar? For buoyant force to become equal to weight, the submerged volume has to be 9/10 of the volume of the ice. No? So if the level of water doesn't reach up to 9/10 the height of the ice cube, then how will 9/10 be submerged? For example, if the level of water is only half x, then the submerged volume is only half of x. So the buoyant force is falling short of weight. No? So it's in contact with the ground. Normal reaction is non-zero. It's like that question we did of the metallic object at the bottom of the tank. Normal reaction is not equal to weight, but it's not zero either because buoyant force is a lot less than the weight. Have you understood now? Okay, very good. Very good. Okay. Let's do the 18th question also. Especially if you haven't done the 18th question, if you haven't attempted it, try out the question number 18. It's based on a similar principle to a question we did last time in class. You remember we did a question where there was a layer of oil floating above water and an object was floating in that combination of oil and water in such a way that part of it was submerged in oil and part of it was submerged in water. So similar concept is there in question number 18. Try it out. Okay, so nobody has worked out the question 18 fully so far. Is anybody got the answer? People are working it out or got the answer? So let's finish this then. Cubical metal block of side length 12 centimeters floats in mercury with 1/5 of the height inside mercury. Okay. So what information that tells us about the relationship between mercury and that metal? It gives us the relationship between their densities, right? If this is the solid metal cubical block, so when it floats in, mercury, it says that 1/5 of its height is inside mercury. So again, it's a bit of a strange situation that 4/5 is outside and only 1/5 is inside. Anyhow, 1/5 or 20% of its volume will be inside mercury. So this tells us that in this case, buoyant force balancing weight means that density of mercury into 1/5 of the total volume, because this is 1/5 of the height. So the volume submerged is 1/5 is equal to density of the metal into V into G. So density of the metal is 1/5 of density of mercury, or 13.6 divided by 5 gram per cc, or it is 6.8 gram per cc. So it's still heavier than water, but considerably lighter than mercury. Okay. Now next up, what we want to do is we want to start pouring water from the side. So when we start pouring water, what will happen to the block? Will it rise up or will it go further down? Can anybody tell me? If I start pouring water onto the mercury from the top like this. Okay, so imagine this is a vessel which has mercury and it has this block of metal floating on it like this. Okay. Now if I start pouring water, what do you think happens to the vessel? Will it, what happens to the metallic block? Will it rise in the mercury or will it go further down? Very good, it will rise, that's correct. Okay. It will rise because, see, because of the concept of hydrostatic, because of Pascal's law principle. Now, what will happen is when we put water at the surface of mercury, the pressure goes up. So at every point inside also the pressure goes up. Now. So the force that is acting because of pressure from below, that will increase. So to counterbalance that, it will have to go up a little bit so that it balances. Okay, so that's why that is what will happen over here. So next up, if we compare this situation with now a situation like this where we have poured a considerable amount of water such that this is disconnected from this. Okay. Yeah, so the water level has reached the top. So the block is about to sink in water. The water level has just about reached the top. But the mercury level, the block itself would have risen as far as the mercury is concerned. Because of what I just told you. The block would have risen up as far as the mercury level is concerned. So this is water and this is mercury. So you can clearly see in my diagram, and I'll show by the calculation why the block has actually risen up. So now let us say that the portion which is in mercury now is some x. So the portion in water is now 12 centimeters minus x, or L minus x. So in this new condition, again the buoyant force is balancing the mg, but buoyant force this time will be equal to what? It will be the pressure difference between here and here. So it will be density of water into L minus x, okay, plus density of mercury into x. So this is that pressure difference into L square. So this has to balance the weight. So now I have to find the value of x. So density of water is 1 gram per cc. So 1 gram per cc into L minus x plus 13.6 gram per cc into x. Okay. This has to be equal to the density of metal into L cube into G. So when we substitute this density of metal, we get L minus x plus 13.6x has to be equal to 13.6 by 5 L. L square G cancels out on both the sides. Okay. So as you can see that 12.6x has to be equal to 13.6 by 5 minus 1 into L. So x has to be equal to this quantity. 1.72 divided by 12.6 L, or 1.72 divided by 12.6 into 12 centimeters. So the level of water that we are pouring, which you can see in the above diagram, is L minus x. So that is going to be here 12 centimeters minus x. So finally the answer that we are looking for is this actually, the height of the water column. So that is your L minus x. So this actually becomes L into which you can further calculate and get the answer. Okay, so people hope these questions and discussions we've had today are 100% clear, because this is precisely the level of questions you should expect at the JEE level from hydrostatics. Okay. Of course, this is 50% of the chapter. Hydrodynamics, actually a little more than 50%, because hydrodynamics has less theory content compared to what we've done in hydrostatics. So we'll finish in another lecture or two entire fluid mechanics. Okay, but yes, there is like easily, you know, a good like maybe 5% kind of weightage on hydrostatics alone in JEE Mains or JEE Advanced. Questions you can expect. So HC Verma is more than enough in this chapter. But if you do the module plus HC Verma, then you are extremely well prepared, especially for JEE Advanced. So most of the concepts are mechanics based, as you can see. In that, you have to just add the concept of Archimedes principle and hydrostatic pressure gradient. Okay. Rest, it's the similar kind of analysis, free body diagrams, torque equations, balancing of forces, those kind of things. Anyhow, so we'll conclude today's session, and next lecture we have in this week, we will pick up hydrodynamics, in which we will study about streamlined motion or steady flow of an ideal fluid, including the Bernoulli's equation, which you might have heard about, right? The very famous Bernoulli's equation and continuity equation. So, for example, the principle of aerofoil, on which aircraft lift, or the thrust force that the wings of an aircraft experience in the upward direction, that is partly the application of Bernoulli's equation. But of course, that is very complex application. At our level, we'll be studying very simple things like streamlined motion of a liquid, like liquid coming out from a small tap in a tank, okay, or liquid flowing through a pipe of variable cross section through a height, etc. Those kind of situations. Okay. So anyhow, that's it for today's session. People, wish you all the best and thanks for attending.
Thank you, sir. Bye, sir.
Bye, sir. Thank you, sir.
Thank you, sir. Bye, sir.
Bye, sir. Thank you.
Bye, sir. Thank you, sir.
Okay, bye, people.